Here we're going to talk about the self-induction. In the last video, we'll talk about the mutual inductance, which is between the two coils. And in this video, I'm going to talk about the self-inductance, that is the inductance of a single coil here. So let us consider we have a coil in which we have passing an oscillating current. That means it is connected to a source which produces an oscillating the voltage. The oscillating voltage produces an oscillating the current. So as the current is passing through this coil, there is the magnetic field, and this magnetic field itself is changing or oscillating. And because the magnetic flux is passing through this coil, there will be an induced EMF, and that is by the Faraday's law. And now the direction of the induced EMF, or this changing magnetic field, will produce an induced EMF which opposes the changes that produces it. So let's try to understand what I mean here. So for example, let us consider a solenoid which is connected to a DC source here, and this is a switch here, and this switch has been on for a long time. And now what we're going to do, we're going to open the switch. Now as we open the switch, you might be thinking the current in the circuit will drop out to zero immediately, but that's not the case with the inductor. It takes a certain amount of time, and the reason is because there is an inductor and it hates changes. It doesn't like to change. It will oppose the changes as much as possible, and the strength of these changes is given by a parameter that we call as a self-inductance. So now let's try to understand a little bit more. So if we open the switch, then the current in the coil, in this coil or the solenoid, starts decreasing. And as the current starts decreasing, then according to the Lenz's law, there will be the induced EMF. According to Faraday's law, there will be induced EMF, and the Lenz's law tell you the EMF direction will be such that it will resist the decreasing current. Okay, so now because the current in this case is decreasing, the induced there will be induced EMF, and the induced current must be in this direction, because originally the current was flowing in this direction. So the induced current must be in this direction here, and this one, and the reason is it would like to have the same magnetic field. It would like to increase the magnetic field because the magnetic field is now decreasing. So it would like to keep the magnetic field up. Okay. So as the current is the induced current will be in this direction. So the polarity, this terminal will be the negative polarity, and this terminal will have positive polarity, because, and that's the reason we have the induced current in this direction here. Okay. So let's take another case here. In this case, we have an open circuit, and this is an inductor, and that's a battery source here. The moment we connect the switch, or we turn on the switch, the magnetic field starts increasing, and it does not increase immediately. It will take some time. Why? Because there is an inductor. It hates the changes. It would like to oppose. So in order to oppose, the direction of the induced EMF will be opposite to the direction of the original current. Okay, so if this is the direction of the induced EMF, so that means this terminal must be positive, and this terminal must be the negative terminal. So I would like you to make sure that you understand these things. So you see the direction of the induced EMF. The direction of the induced EMF is in such a way that it always tries to resist the changes. Whether if it is increasing current, then the direction of the induced current will be opposite to the original value. If it is decreasing if the current is decreasing, then the induced EMF will be in the direction of the original current here. For example, this is the original, the current direction, and then induced current is also in the same direction because it like to resist the changes. Okay, so now how do we define the self-inductance? The self-inductance we define as the magnetic flux passing through that coil and divided by the current passing through this one. So the magnetic flux passing through this coil and divided by the current. So that we call as a self-inductance. That's the mathematical definition. And what are the unit of the self-inductance? The unit is Henry, just like the mutual inductance. Okay, and there are the units of the self-inductance. And I would also like to say something about the self-inductance here, or the other equation of the self-inductance. So by the Faraday's law, we know that the induced EMF, this E we call as an EMF, or the induced EMF, is the rate of change of magnetic flux, d phi over dt. That's the rate of change of magnetic flux. And this negative sign simply means the induced EMF, direction of the induced EMF or induced current, will always try to resist the changes. That's the meaning. And we know the the L, which is the self-inductance, is given by phi over I. So I can write down in terms of phi, which is Li. So if I plug this equation 2 in equation 1, I will have another equation for the induced EMF, and which is in terms of the current. So that is induced EMF, self-induced EMF is the negative L times di over dt. So remember that equation. So this is it for the this video here, and in the next video we're going to talk about the self-inductance of a solenoid, or how we're going to find out the value here. And just for your understanding, this L, which is the self-inductance, does not depend upon the voltage source or the current passing through it. It is simply the geometrical parameters. So thank you so much, and I will see you in the next video.